Hello and welcome back. Today I'm going to be discussing about the various types of amplifier classes commonly used to amplify audio signals. I'm going to go through the A, B, G, H and D types. Look at how these operate and what makes one different from the other. So if you're curious about this, then keep watching. So we can start off by looking at the A-class amplifier. Basically, you need a single transistor in a common emitter type circuit. You get your input signal through the base and then you collect your output signal from the collector. So what makes this type of circuit special? What makes the class A circuit special? Well, for that we need to analyze a bit how the transistor works. The transistor has three modes of operation. Cutoff, in which the base signal is too small to actually switch the transistor, so you get a certain base emitter voltage, but you have no collector current. Then you have the active region, in which the input signal actually creates an output signal on the collector, and then you have the saturation mode, in which the base emitter signal no longer creates any more variation on the collector. But to keep the transistor in the amplifier mode, we need to keep it in the active region. Especially if we look at this graph, we need to keep it in the linear amplification region. Therefore, to keep the transistor in a class A type of amplifier, we need to bias it with a certain signal so that it stays in the middle of this linear portion. So even if you have a signal, even if you don't have a signal, there will be current passing through the transistor. Now the signal that you are adding will just move our bias point left and right on this curve, giving us our output amplified signal. So this will make our amplifier very linear. We're only using a single transistor in its linear region, so there's nothing that would distort or modify our signal. But it's also a very inefficient way of using a transistor because we always have current going through it. So we're always wasting some power. So let's see how this circuit works in reality by simulating it. So this is the basic amplifier that I will be simulating. We get our input signal 1 millivolt 100 Hz signal. We're supplying it with 10 volts and then we have our output. So let's quickly look at how this thing is working. So we have these two resistors to set up the bias point, so the static operating point of the transistor, around 700 millivolts. And then when we add our signal, the two voltages are summed together, forming this sine wave with the 700 millivolt offset. And this is what is going into the base of the transistor. And this is creating a collector current, which has a fixed value around the operating point when there's no signal, around 6.6 milliamps. And then based on our input signal, it oscillates up and down. And this is what we see at the output. So we have our output signal, the sine wave, which is a copy of our input signal. Now, one thing to mention about this amplifier, since it's a common emitter amplifier, let me just modify the input signal to make it more clear. The output signal is 180 degrees out of phase with the input. So this is a typical characteristic of the common emitter amplifier. And as we said, the current going through the transistor is always there, so you never get to 0 milliamps, making this quite a wasteful amplifier, but a very good quality amplifier. Now if you want to make a class A amplifier at higher powers, you will be replacing the collector resistor with a constant current source. So you will have something like this. We're still getting the same input signal, the same resistor divider to set up our operating point of our low side transistor, but in the collector we have this constant current source. The output is the same, the circuit behaves in the same way, but the constant current source gives us much better linearity when working with larger voltage swings. So when you're building a higher power amplifier, this is the sort of circuit you will be seeing. So having two transistors on the output doesn't mean it's a different class of amplifier. The class is determined by how the circuit actually works. Let's move on. So let's have a look at the B-class amplifier, but first let's just remember the operating modes of the transistor. So we got our cutoff region, in which the collector current is not proportional to the base emitter voltage. We got our active region, where the collector current is directly proportional to the base emitter voltage, based on the gain factor. And then the saturation region, in which the collector current flattens out and is no longer proportional to the base emitter voltage. Now, the main problem with the Class A amplifier was that the transistors were always using power, with or without any signal. So, to counteract this, the B-class amplifier was designed, which doesn't use any sort of current when there is no signal, and the only current going through the output stage is the current needed by the output load. So how does one of these stages work? Well, basically, you take your input signal, basic sine wave, chop it off into two pieces, so you got your positive half and you got your negative half. You take these two signals, amplify them with two different transistors, so you amplify the positive end, you amplify the negative end, and then you recombine the two into your sine wave, just like the signal you had at the beginning. So how do you keep this sort of amplifier from using any sort of power when there's no signal? Well, it has to do with this part, the amplification stage. Basically, what you do, you take your half signal and amplify it directly with your transistor. That means that when you have very small signals, your output signal is not amplified at all. Only when the signal is large enough does it reach the active region of the transistor and it becomes amplified. So your output signal will be just like your input signal, only with the beginning of it chopped off. So the voltage needed to actually put the transistor into the active stage will not be seen at the output. That means that our input signal, which is a perfect sine wave, will look like this at the end, with the middle bits, with the low voltage bits cut off. This actually being the voltage needed to switch on the transistor. So let's see one of these circuits actually implemented in a simulation. Now in its most basic form, the B-class amplifier looks something like this. We still have our two resistors giving us a voltage to set the static operation point at half the supply voltage, onto which we add our input signal. And we use this signal to drive the transistors. So let's see this thing in action. We have our input signal, we have our drive signal to the transistors, and then we have our output signal. Now what we can see immediately is that the output signal is around 0.7 volts lower than the supply signal. And when this difference goes around the 5 volt mark, so the middle of the supply voltage, then the output becomes stationary at 5 volts. So each of the transistors can only conduct current when their base voltage is higher than the output voltage by the 0.7 volt mark. So this means that our output signal is distorted, so the middle bit has been removed, but this also means that the current going through the transistors is zero unless you actually want to have current going to the output. So on the high side transistor we have the positive currents going, and through the low side transistor we have the negative currents. And the sum of these is the current going through our load. And other than that, there's no current pulled by the amplifier. So there's no current in between these sine wave peaks, making the B-class amplifier much more efficient than the A-class. Now, because the Class B chops off a bit of the signal, it doesn't sound very good. It's not a very good audio amplifier, especially if you're into high fidelity audio. So what was created was the combination of the Class A and Class B amplifiers, the Class AB amplifier. So what this does, it takes the normal operation of our Class B amplifier, in which we took our input signal, chopped it in two, amplified it with two different transistors, and then recombined it into an output signal, and combines this operating principle with the Class A amplifier, in which the transistor is always biased, no matter what the input signal is. Basically, you take these two operating curves of the transistors and you overlap them a bit. And you get something like this. Basically, your input signal when you are working with very small signals is amplified by both transistors, and only when you have large voltage deviations are you being amplified by only a single transistor. Basically, by having this overlapping, the gain factor of your amplifier becomes linear, since the sum of these two exponential curves can be approximated to a linear amplification factor. So with this type of amplifier you will still have a bit of current going through the circuit when there's no load, but it will be much smaller than the Class A amplifier. But you will also have very high efficiency, so most of the current going through the amplifier is the current going through the output load. So let's see this thing implemented in practice. To overlap the operating points of the two transistors, in a Class B amplifier, you end up adding a voltage to the signal to drive the upper transistor and then subtracting a voltage to drive the lower transistor. Basically, we can see again our input signal. It goes into the biasing circuit, so we have it around 5 volts. And then if we look at what goes into the first transistor, we see that it's the same signal but with around 0.7 volts added. So the voltage drop on a typical PN junction. Now for the low side transistor we do the same thing, only we subtract it. That means that the voltage going into the second transistor is our input signal minus 0.7. Now when these transistors will be conducting, the output voltage will be the input voltage minus 0.7. That means that from the upper voltage we will subtract 0.7 and then from the lower voltage we will add 0.7, giving us again the input signal. And in this way the output signal is a perfect sine wave, so it doesn't have any more discontinuities through the 0 point. Now if we look at the current going through our circuit, we can see the load current, and then if we check the two transistor currents, we will see that one of the transistors is being driven through one half of our signal and then the other through the other half of our signal. But even when there's no signal, there is still a bit of current going through the transistors. So we got this 0.9 milliamps as static current. But this is still much better than our A-class amplifier, in which the static current was half of the maximum current that could go through our circuit. So this circuit is still more efficient than the A-class, but it has a much better output response than the B-class. Now one thing to take into account if you're building this sort of voltage shifting is that the two PN junctions, so the one that you are driving in the transistors and the one that you are using to make the offset, need to be at the same temperature. And that is because the voltage drop on the PN junction is temperature dependent. So what I got here is the same circuit, only I told the diodes to be at 25 degrees and the transistors to be at 80 degrees. Now if we look at the output, it's still okay. So the amplifier is still amplifying, but if we look at the currents, we can see that the static current is huge. You have 20 milliamps going through the circuit when there is no input signal. And that is because the voltage drop on our diode is much larger than the voltage needed to put the transistor into the active region. So we have a very high static current. That's why you may have noticed in certain amplifiers that the output stage is on a radiator together with another small transistor. That transistor usually takes the role of these two diodes, and you need to keep the two junctions at the same temperature, even when your output transistors will heat up from operation. Now, one of the things that makes the Class AB amplifier still inefficient is that the current going through the load is the current coming from the supply. Now, this is normally a good thing, but imagine it this way. You've got a very high voltage supply, since your amplifier is for very high powers, so let's say 80 volts. You've got a very small signal that's being amplified, let's say 1 volt, and you're using your amplifier at these small signal levels. So you're using it inside your house or something, so you don't want to have it cranked up. But the same amplifier you also want to be able to use when you're at a party or something. Now in this case, since we're supplying at 80 volts and we're only using 1 volt, the rest of the 79 volts is a voltage drop on our transistor, meaning that we have very high power dissipation. So at light loads, this sort of amplifier is highly inefficient. Now to fix this, the class G amplifier was created. Basically what this does is keep the basic AB class output stage, keep your first supply rail, but also use a switched higher voltage supply rail. And this second supply rail is only used when your input signal is high enough. So if your input signal requires more than your basic V plus voltage, then you will switch to this double V plus or whatever value you need. This voltage can come from a transformer, from a voltage booster, charge pump circuit, or whatever. And this is why this sort of amplifier will be a bit more efficient than the classic AB, because this will be able to supply high efficiency both at light loads and at high loads. So here we can see this principle put into practice. We still have our input signal and the two diodes to create an offset to it to drive our AB class amplifier. We got our output load and we're supplying this time from a differential supply. So we got a plus and a minus supply rail. I put as an arbitrary value plus and minus 10 volts. Now normally this is what is going to supply our output stage. But in case we have very high input signals, we will be able to drive this transistor. So if the base of this transistor sees the supply voltage plus around 0.7, then this will turn on, allowing this high side transistor to supply our output stage with a much higher voltage. So this pair of transistors will only turn on if our input signal is high enough to drive it. Other than that, the output stage will be driven only by our basic supply voltage. And then we have the same principle on the load side. So let's see this thing in action. Right now I'm driving with a small voltage, so plus minus 5 volts. We have the same thing on the output, so the amplifier is still amplifying. And if we look at the supply of our high side transistor, we see it's around 9 volts. So we have our 10 volt supply minus what we have as a voltage drop on our diode. There's no current going through our high side switch. Well, there's around a few hundred nanoamps, but that's just because I made a very simplified circuit here. Now let's see what happens if we have a much larger input signal, let's say 11 volts, which is larger than the first supply voltage. Now if we look at the output, the amplifier is still amplifying, so we still have our basic operating principle. But if we look at the supply voltage for our output stage, we see that it jumps. It jumps from the base 9 volts at which it is supplied normally to 20 volts, so our secondary supply voltage. And we see that this happens only when our input signal exceeds a certain threshold. So when our input signal exceeds around 9 volts, then the supply switches to the second supply voltage. So the output current, the current going through our load, is supplied from our first supply when low voltages are used, and then it's supplied by our secondary supply when higher voltages are used. And we see this switching going from one of the supplies to the other, but still maintaining a constant output waveform. Now, the final type of analog amplifier that I wish to talk about today is the class H. Basically, it takes the class G amplifier and improves its response. The problem with the class G amplifier is this switch. Basically, the supply voltage to your output stage, which is the basic class AB, jumps from your initial voltage to a different voltage, and this jump can affect the output signal. So to fix this, the class H has a bit of a different approach. It still uses the same multiple voltage supply approach, but this time your second voltage is not switched directly onto the supply of the output stage, but rather you're building a linear supply whose output voltage varies in accordance to the input signal. So your output stage will only be supplied with a voltage that's the input signal plus a bit, so 1-2 volts. it will never jump directly from one voltage to the other. It will slowly increase and decrease according to the output requirement. This will give you much better linearity and much less noise on the output. So this is what this kind of amplifier looks like put into practice. We keep our base AB class amplifier in the middle, we have our initial supply voltage, and when our input signal reaches sufficient amount of amplitude, our secondary supply gets utilized. But because of the configuration we are using, the supply that goes into our output stage will only be the input signal plus a certain amount, so 0.7 in this case. So let's quickly look at how this thing is running. So we have our more than 10 volt signal, our first supply is at 10 volts. The output is still working, so the amplifier is still working without distorting the signal too much. And we can see that the current going through our output load is coming half from our first supply voltage, so at low voltages it's coming from the low voltage supply, and at high voltages it's coming from our high voltage supply. But if we look at the voltage going into the output stage, we can see that it goes from 9 volts to around 12 volts. So it doesn't jump from 9 to 20 like before. And this voltage increase is proportional to our input signal. So we can see that the supply voltage, when we exceed a certain threshold, ends up rising proportionally to our signal. We no longer have the jump between two extreme voltages. And this sort of linear variation of the supply voltage keeps the output signal unaffected. So this sort of circuitry will keep the benefits of the G-class amplifier, so by using multiple supply rails, but it will also keep the output signal unaffected, like a typical AB class amplifier, since there's no sudden variations of the supply voltage. And this is basically the last type of analog amplifier that is currently used in audio applications. Now there's one more type of amplifier to discuss, which is a digital type of amplifier. So until now, I've discussed analog amplifiers. What makes an amplifier be analog? Well, the input signal is analog, so like a basic sine wave. The output signal is also analog, but everything in the middle that goes on inside the amplifier is also of an analog value. So it has to be always proportional to the input signal and can take any sort of value between 0 and 1, for example. So there's an infinity of values that this signal can take. Now in the case of the digital amplifier, you still have the same analog input and analog output, but you get a digital signal in the middle. So you got well-defined discrete values, zeros and ones. Now the advantage in this case is that it's very easy to amplify this sort of values. You don't have to worry about linearity, distortions, things like this. A 1 is a 1 and a 0 is a 0. The only problem with this type of amplifiers is the going from the analog to digital and from digital to analog. This is where your distortions and nonlinearities are going to happen. And the prime example of such an amplifier is the D-class amplifier. So let's have a look at that. So this is what your basic D-class amplifier looks like. I didn't build it completely out of components. I also took some liberties with some dependent and independent voltage sources. So let's have a look. We have our input signal, same as we did before. We need a sawtooth generator or a triangle wave generator that goes at high frequency, so much higher than your useful audio signal. You compare the two, and this is where you turn from the analog signal to the digital, since the output of the comparator will be either a 1 or a 0, in this case 10 or 0, and then you take this digital information, drive an output stage, still keeping the signal in the digital form, and then you integrate it and filter it using a low-pass filter, and turn it into an output signal, which should look the same as the input signal. So let's see if this thing actually works. So we can see our input signal, and then the much higher frequency generator, and basically what the comparator will do, will compare the two signals. If our useful signal is higher than the generator, then it's a 1, if it's lower, then it's a 0. Basically we end up with something like this. So this is a pulse width modulated signal. It's either 1 or 0. The frequency is always constant, so it has the frequency of our generator, but the duty cycle is directly proportional to our input signal. And this sort of signal is the type of signal that you can amplify really easily. And once we pass this through our output stage, we get the same thing. Now the interesting bit is what happens when we pass it through the low pass filter. Actually, you can look directly on the output, and if we zoom out a bit, we will see that we're slowly getting back our input signal. So this sine wave is the same as our input, only it's inverted, so it's 180 degrees out of phase. That's because of how I set up the comparator. Now, one thing that you may already notice is that the output signal has this bouncing in it. This is because the low pass filter is not doing a good enough job. And this is one of the problems with the D-class amplifier. Apart from your useful signal, so the big sine wave, you will also have these artifacts left behind from the switching action of the comparator. What makes this type of amplifier not be as high fidelity as the analog types is the sampling rate. Basically, how many times a second do you look at the input signal when you're turning it into a digital signal? This is based on our local oscillator frequency. During one period of oscillation, you will only get out one value through the comparator. You cannot get more than one value during a single cycle. And this is where you end up affecting the quality of your audio signal. You're chopping your pure analog signal into digital bits. Now, what makes the D-class amplifier special is the efficiency you can obtain. With the A-class amplifier, you had a maximum theoretical efficiency of around 50%. With the AB-class amplifier, again, the maximum theoretical efficiency is around 78%. With the D-class amplifier, the maximum theoretical efficiency is 100%. And why is that? Well, it's regarding the power stage. Since you're working with digital signals, so zeros and ones, either one transistor is on or the other. You're never in the active region of the transistor. It's either saturated or cut off. Now, especially with field effect transistors, with MOSFETs, when these transistors are saturated, their on resistance is extremely small, so in the order of milliohms. So basically, even if you have very high currents going through the switch, you'll have extremely small losses. And basically, all of the energy taken from the supply will be given to the output. You will have no significant losses on your low-pass filter since these are active components, and you will end up with very high efficiencies. In practice, you can easily exceed 95%. And that's what makes the D-class amplifier highly used when high efficiency is required or when extremely high output powers are required, when a typical class AB would just destroy itself by overheating. And basically, this is how the D-class amplifier works. Now, when talking about amplifiers, of course there's a lot more to say, but I will get to that another time. So if you're curious about the simulations that you have just seen in this video, then you can take a look in the description where you have a link to them. Hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching and see you next time. Bye bye.